welcome back. So, before the break we were talking about the option Greeks. I started introducing the concept of option Greeks, and we started with the Black-Scholes model, and if I wrote d1 as log of s naught or s upon k plus r minus q. Now, this q is something interesting, plus 1 by 2 sigma square t divided by sigma root t. Now, q represents the yield that the underlying asset may provide during the life of the option. If the yield is 0, we have the standard expression for d1, that is r plus 1 by 2 sigma square t in this expression. But however, if there is a yield in terms of percentage given by q, for example, on a stock index or on a foreign currency underlying asset foreign which has a interest rate, q will be capturing that particular component of yield. So, there would be obviously another additional term if you want to include q as the yield on the underlying asset. Now, then I talked about the expansion, the Taylor expansion of the call price about a certain given value. This left hand side represents the call price at a slightly displaced, a slightly shifted value of these parameters from the original value. The original value of the call price was C0, and now there has been a shift in various parameters that influence the option price, and the shifted value of the call price is given by this C. This delta C, delta T, delta sigma, delta R and delta Q represents the respective shifts. Now, if you expand this as a Taylor series, you get this full expression, and this enables us to define certain fundamental terms. And what are those terms? These terms are essentially the partial derivatives of the call price with respect to these variables which influence the call price. The stock price, the time to maturity or the time expired, either case, the volatility of the stock, the risk free rate and the yield. As you see, now there are two important things. One important thing is that other than this expression gamma, these are all first order derivatives. And the second thing is, it is certainly not at all necessary and mandatory, obligatory that we should truncate this expansion to this particular point and forget about all the remaining terms. With the increase in computing power, you can obviously obtain higher accuracy by including more terms of the Taylor expansion. But by tradition or by convention, these quantities delta, gamma, theta, vega, rho and phi constitute the fundamental set of option Greeks which are conventional in use. Of course, as I reiterate, this set has been extended with the increase in computing power to many more. As you can see in this particular slide, we have something called the inertia, we have got something called the Volga, the charm, the Vita, Vana and even more than that. So, we are not confining ourselves to the first order derivatives, we are not truncating the Taylor series at the earlier point, this point, we are including more terms of the Taylor series in order to enhance our accuracy level to whatever level we want to choose or we deem appropriate. This is the set of the current option Greeks which are in use. Nevertheless, I reiterate that the fundamental ones are delta, theta, vega, rho, phi and gamma. These are the conventional ones, these are the most important ones, the most relevant ones. The others are more of cosmetic nature, but nevertheless they contribute to enhancing accuracy. So, the option Greeks are measures of sensitivity. See, when they are partial derivatives, what are partial derivatives? Partial derivatives are measures of what are they? They are the ratio of the changes in price over of the call option or of any option or any position in fact. with respect to a particular influencing variable, that ratio being calculated over an infinitesimal interval or infinitesimal change in the independent variable. So, in that sense, the Greeks are measures of sensitivity of the position's value to changes in any of the variables that contribute to the position's market value. So, they are partial derivatives, and they now we talk about each one individually. The option delta, what is the option delta? The option delta represents the partial derivative of the position with respect to the underlying asset, with respect to the price of the underlying asset. So, it represents the slope of the curve of the price curve of the position, or the value of the position with respect to the price of the underlying asset, value of the position with respect to price of the underlying asset. For example, for a call, it would represent the slope of the call price with respect to the price of the underlying asset. In mathematical terms, it is the partial derivative of the call price with respect to price of the underlying asset, or partial derivative of the put price with respect to price of the underlying asset, as the case may be. Now, we worked out this value earlier in the context of Black-Scholes equation, you would recall, and we found that delta is equal to phi of d1. And remember, phi is the cumulative normal distribution of the standard normal variate. Now, it is very clear that phi cannot increase, cannot be outside this interval. Phi must lie between 0 and 1, and by as a corollary, delta must also lie between 0 and 1. As far as the call option is concerned, for the put option, the delta lies between -1 and 0. And in fact, from put call parity, it can be established that the sum of the absolute values of the delta of the call option and the delta of the put options is equal to 1. So, as you can see in this diagram, this is the call price, this is the stock price. The call price is shown by this particular curve. This is the curve representing the call price. Remember, call price is not linear function of the stock price. Call price is not a linear function of the stock price, and that is very clear if you look at the Black-Scholes expression for the call price, that it is not linear. We have got C is equal to what? C is equal to S phi d1 minus k e to the power minus RT phi d2. So, if you plot a curve between C and S, this factor is certainly not constant, and the d1 is not independent of S, therefore, phi d1 is not independent of S, and therefore, the coefficient of S is not independent of S, and therefore, it is not a linear graph. It is a curved graph, and the slope is referred to as delta. Now, one immediate fallout is that because this is a curve, the slope at every point is different. In other words, delta is different at different prices. I work out the delta here, I get a certain value. I work out the delta here, I will get a different value. I work out the delta here, I will get a different value. So, delta value also changes from point to point along this price curve. And in fact, this change in the value of delta is captured by the second derivative, which is called the gamma, which we shall talk about soon. Now, delta of call options. Now, when the stock price increases, the value of the call option also increases, and therefore, the value of delta is invariably positive, as I mentioned earlier, because an increase in the stock price is reflected an increase in the call price, and therefore, value of delta also increases, value of delta is positive. And this is interesting. You see, delta is given by phi d1. Now, phi d1 is the cumulative normal distribution. So, higher the value of d1, higher will be the value of higher will be the value of phi. You see, phi of d1 is given by what? Is equal to 1 upon root 2 pi integral minus infinity to d1 e to the power minus 1 by 2 omega square or z square, you may like whatever you like, d omega, right. Now, as d1 increases, phi d1 has to increase, because the upper limit of the area increases. If you have this d1 and then this d1, obviously this area this d1 area is more than this d1. So, higher the d1, higher is the phi d1. Then secondly, higher the s, higher is d1, higher the s, higher is d1. So, what do we infer? Higher the s, higher is delta. So, as the stock price increases, delta also increases. In other words, gamma is positive for a call option. So, this is the relation for between delta and various types of option in relation to strike price. We have options which are out of the money when this for example, the call is let's say written at 50 and the stock price is at 0 or 10 or 20, that is when the suppose this is the situation. Suppose the strike price is 50, k is equal to 50 and the current stock price is say 10. What will happen? Suppose the stock price increases from 10 to 11. Will it significantly affect the probability of the exercise of the option? The first thing is, when this kind of a situation prevails, it is almost certain or it's pretty much clear that the option will not be exercised on maturity. It is very likely at least that the option will not be exercised on maturity. And if there is a small increase in the stock price, that is not going to significantly affect this perception that the option is not going to be exercised. And therefore, because that perception is not going to change, the value of the option is not likely to change much. And as a result of which, delta of out of the money options is pretty close to 0. However, as the stock price moves towards this, let us say around 48 or 47, then there is a significant probability that the option could end up in the money and therefore could be exercised. And a small increase in price in that situation could enhance that probability significantly, and therefore, the price of the option would be significantly impacted by a small increase in the underlying price, as you can see in this region. But however, now what happens? Let us see what happens when the stock price goes to say 100. Now, you are pretty much sure that the option will be exercised. And again we have a situation where if the option is sure to be exercised, a small change in the stock price is not going to affect that probability or that perception significantly. And therefore, the change in this value of the option is not going to be significant. However, what happens in this situation? Because the option is sure to be exercised, 1 unit change in the price will be perfectly reflected, mimicked by the price of the option, because the payoff of the option, you see, the probability of exercise will not change significantly, but the payoff of the option will increase in line. You see, the payoff of the option is given by ST minus K. So, if you are sure of getting this payoff, 1 unit increase in the stock price will also cause a 1 unit increase in the price of the call option, and therefore, the delta in that situation would be 1, not because of the probability impact, but because of the impact on the payoff. In other words, in a nutshell, what happens is, for out of the money options, delta is close to 0, because price is not likely to change, the options are not likely to exercise, payoff is going to be 0, and small change does not affect the probability and the payoff. But here the payoff is affected, although the probability of exercise is more or less the same, it is almost certain. So at this point the delta becomes 1 and the delta remains more or less somewhere around 0.5 or thereabouts in between. As a general rule, in the money options will move more than out of the money options, as you can see here. Out of the money options the variation is small, in the money options the variations is relatively large. That is because delta in the case of in the money is close to 1 and delta in the case of out of the money options is close to 0. Now, what happens in the case of the put option? In the case of the put option, the situation is reversed. When the price of the underlying rises, the put option tends to go out of the money. And see, first thing is, as the price increases, the price of the put option decreases, so delta is negative. In fact, it ranges from -1 to 0. Put delta will increase from -1 towards 0 as the option goes from out of from in the money to out of the money. The out of the money delta of out of the money put options is close to 0. Delta of in the money put options, if it is deep in the money, is -1. Why it is -1? Because the option is surely likely to be exercised, and if a put option is exercised, the payoff is k minus st, and because of this minus sign, if st increases, the payoff decreases, and they are move in opposite directions, and therefore delta turns out to be -1, provided this is almost sure, or provided that the option is deep in the money. And as the option moves from out of the money to in the money, the delta changes from 0 to -1 and vice versa. Now, what about delta and expiration? That is interesting. See, you have to look at it backwards. You see, please note, time to expiration is increasing here, but in actual fact time to expiration decreases. So, we have to look at this graph while interpreting it in this way. And therefore, as time to expiration decreases, what happens? In the money options tend to move towards 1, that is natural, because the payoff, what is the payoff? Payoff is st minus k. As you are approaching the maturity of the option, this payoff becomes more and more certain. And because this payoff becomes more and more certain, the delta tends to move more and more towards 1 because of this factor st. So, if you differentiate it with respect to st, you get +1. It is as straightforward. So, if you are moving towards this maturity, for example, at maturity your payoff is st minus k, and therefore delta would be 1 for an in the money option, because you are surely going to exercise it. However, at the money options, the payoff is again the delta is again fluctuating or changing rapidly, but it is not necessarily moving upwards. It could move down, it could move upwards also. It could, the tendency is usually to move down. And in the case of out of the money options, it is very clear that the delta has to go to 0 at maturity, because if the option is out of the money at maturity, the payoff is 0, and if the payoff is 0, the price change would be 0, or you are almost certain not to exercise it, and therefore the price change would also be closing in on 0. Therefore, short term options will react more than longer term options. As you can very well see, all these 3 options, the slope is higher towards maturity. As the time to maturity is decreasing, the slope is higher, although the slope is in different direction, but the magnitude of the slope is definitely more. And therefore, what does it mean? It means that the price of the option will change more given a same change in the price of the stock. Now, delta and put call parity. I mentioned earlier, in fact, that the absolute value of the delta, the sum of the absolute values of the deltas of the put option and the delta of the call option sum to 0. This is quite simple to see. What do we have? From the put call parity, we have C plus k e to the power minus r t is equal to p plus s naught. So, if you differentiate with respect to s, we get del c by del s. This will contribute 0. is equal to del P by del S plus 1, or del C by del S minus del P by del S is equal to 1. Or now please note one thing, del P by del S is negative, and therefore del P by del S is equal to minus of mod del P by del S, whereas del C by del S is equal to mod of del C by del S. You put these values here, what do I get? Mod of del C by del S plus del P by del S mod is equal to 1. This is what we were saying. The sum of the absolute value of the delta of the call and the absolute value of the delta of the put option is equal to 1. But I reiterate, this is an important thing. The delta, you see, because the curve is nonlinear, the curve has a curvature, and because the curve has a curvature, therefore delta changes from point to point, and therefore with every price change the delta also changes, and therefore if you are looking at a large range, it's something like, when we talked about duration, we had a slightly similar scenario. Although the curve was nonlinear, the shape of the curve was different, but the scenario was more the same. The curve had a curvature. Here also we have a curvature, and we have, because the curvature is there, the delta at different points is same. Therefore, if you are working out the change in price by using only delta, there would be a significant error if the change in price of the underlying asset that you are using has a significant value. Now, delta hedging is very interesting. You see, what is delta? Delta is equal to, let's talk in the context of call options. So, delta hedging means what? What is delta? Delta is the change in value of a call option due to a small change in value of the underlying asset, change in price of the underlying asset. In other words, we can say that if we did it in the Black-Scholes model, in fact, while working out the PDE, if you construct a portfolio of one call option and delta units of the stock, you have a delta hedged portfolio, and we showed that in such a situation we have a portfolio where the risk or the diffusion terms cancel each other, and as a result we assume that the portfolio was risk free, but the basic thing is that the portfolio is risk free over infinitesimal time. It is not risk free over a sustained period of time. Anyway, so that is what is delta. Delta is the number of units of the stock that need to be included in a portfolio of calls, obviously at an opposite position, in order to make a delta neutral or a delta risk free portfolio. Let us call it delta risk free portfolio. Now, so far so good, but I just also mentioned that as the stock price changes, delta changes. So, what are these two things? Number one, that we can construct a delta risk free portfolio by using one unit of the derivative and let us say long derivative and short delta units of the stock. And the second thing, that for every time a price change occurs in the price of the underlying, delta changes. So, if you combine these two things, then we are in trouble. The trouble is that because delta is going to change after every movement of this stock, the portfolio that we have constructed risk free will go out of balance or will go out of risk freeness as soon as there is a change in price. Because if it is risk free at a given delta and a price change occurs, then because of the change in delta, there will be a new risk free delta coming into play, and you will have to revise your composition of the portfolio in order to to recreate a new delta risk-free portfolio. In other words, you have to rebalance your portfolio after every stock price move, which is a really impracticable exercise. So, the bottom line is, if you have a delta neutral portfolio or a delta risk free portfolio, that delta risk free portfolio remains risk free only for infinitesimal changes in the stock price, not for large changes in stock price. Large changes in stock price will not remain or will not be neutralized inter se between the price of the derivative and the price of the stock. That is very important. That is where all the problems creep in. Therefore, you have to, in a sense, to be risk free over sustained regions of stock price movements, you have to rebalance your portfolios frequently, very frequently. How frequently is the question? Well, that depends on the rate at which delta would change with respect to the stock price, and that is captured by a new option Greek which is called gamma, which is simply the rate of change of delta with respect to the stock price. So, if gamma is small, what does it mean? It means that delta is changing very little due to changes in stock price, and therefore, the requirement of rebalancing would be much less. However, if gamma is large, then we are in trouble. Then the delta values would change very significantly for every change in stock price, and therefore, a portfolio which is delta neutral at one point in at a particular value of stock may not remain so at another value of stock, because delta would have gone out of phase altogether. So, these are some delta positive strategies: long call, short put, bullish call spread, bullish put spread. We are all familiar with these. These are some of the delta neutral strategies: iron condor, butterfly we have talked about, long straddles, long strangle, long calendar spread. I have not talked about iron condor, so I will give a brief introduction on this. An iron condor consists of 4 options. Just like our butterfly spread, it also consists of 4 options. You will recall box spread also consists of 4 options. Iron condor also consists of 4 options: long OTM, OTM means out of the money put at price K1, short or out of the money put Y at K2, short OTM call at K3, long OTM call at K4. Let us first look at the initial investment. He says long OTM put X at K1 and short OTM put at K2, and he also says that K1 is less than K2. Now, we talked about earlier that put prices are in tandem with the exercise prices. Therefore, the put price of this, let us say Px is less than the price of this, let us say Py. Since you are short in Y and you are long in X, so what will happen? You are paying this is an outflow, this is an inflow. So, the combination of these two is a inflow. So, let us call it positive inflow, or positive flow of inflow is obviously positive. Now, let us look at these two. In the case of a call option, if you remember, we said that the call premia are opposite to the exercise price. Why? Call is the right to buy. So, the lower the exercise price, the more valuable it is. So, this is more valuable, this is more valuable than this one. In other words, A is more valuable than B, and because you have shorted A, so you will get more, the inflow will be more, and because you have taken long B and you have paid less. In other words, this will also result in a positive flow. So, the net flow of both these quantities or both these sets, and therefore, the aggregate is going to be positive. Let us now look at the payoff. Again, we divide our stock prices into various segments, various partitions: 0 to K1, K1 to K2, K2 to K3, K3 to K4, and greater than K4. Now, as far as X is concerned, it will be exercised between 0 and K1, and we will get a, because it is long, you will get a pay in of K1 minus ST. As far as Y is concerned, it will be exercised in both these cases. Why? Because if the strike price, if the stock price is lower than the strike price, then the option will be exercised, and what I will get is ST minus K2 here, and again if the price is between these two, again I will get ST minus K2. And what about the short call A? Well, if A has the exercise price K3, so only if the stock price is greater than K3, this will be exercised, but because it is short, the payoff will be K3 minus ST, K3 minus ST in both cases. And similarly for the long call B, it will be exercised if the stock price ends up greater than K4, and with this we have this. If you aggregate all these cash flows, what you find is that in every scenario except when the stock price lies between K2 and K3, the payoff is negative. There is only one scenario, this is the best case scenario, and in the best case scenario the payoff is 0. This is the maturity payoff. But remember that you made a profit when you created the strategy. So at that point you had a positive cash flow, and at this point you are faced with a negative cash flow in most scenarios, except in one scenario where the best case scenario where your profit or loss is 0. In other words, if the stock price ends up between these two, between K2 and K3, you make a loss of 0, and you run away with a profit equal to the difference between the premia of the two calls and the premia of the two puts that constituted the strategy at the time of conceptualization. So this iron Condor at maturity does not give you a positive payoff, but it does give you a positive inflow at the time of creation of this strategy. We will continue from here on. Thank you.